everybody. So my name is Juan Carrasquilla. I'm from the Vector Institute and the University of Waterloo. I'd like to thank Professor Masatoshi Imada for the kind invitation, and I apologize for not being able to make it to Japan in person. So I hope you enjoy anyways this presentation. So here we go. So today I'm going to tell you about the machine learning perspective on the many-body problem in classical and quantum physics. And before that, let me acknowledge my collaborators, so Leandro Aolita, Roger Melko, Giacomo Torlai, Esen Hetami, Kelvin Chang, Giuseppe Carleo, Matthias Troyer, Peter Brocker, Simon Trebst, and Guillermo Mazzola, which are the people who have been working with and along this line of research. So I'm going to introduce my talk using the many-body problem in quantum mechanics, where a generic specification of the quantum state requires resources exponentially large in the number of degrees of freedom n. So for instance, if you want to specify the state of a spin 1/2 system with n spins, you need a vector with 2 to the n complex valued entries, right? So that the problem is so large that even with today's best supercomputers, we can only solve the wave equation for up to maximum of 45 particles or 45 spins, right? So that's using our best supercomputers, but and the problem grows so dramatically fast that storing the state of a 273 spin system requires a computer with more bits than there are atoms in the universe, right? So, and yet we are interested in problems that are technologically relevant in chemistry and condensed matter physics and in quantum computing that are way larger than 273 spins. So we want to go beyond that. There's quantum computing, of course, which promises to help us solve some of these problems, but we're still trying to figure out how to build those. However, there's still hope for classical algorithms, and that's what we're doing right now, right? Like and everybody else in quantum information and condensed matter, because nature is sometimes compassionate or benevolent, and many-body systems can be typically characterized by an amount of information smaller than this maximum capacity of the state space, this 2 to the n components. And this is what we exploit, for instance, in quantum Monte Carlo simulations and other numerical methods based on tensor networks, for instance, right? Like, so we exploit this structure in this more physical states, and in quantum Monte Carlo, for instance, we do a stochastic sampling of this large state space, and we're able to compute correlation functions and other quantities that are useful and that allows us to understand and to study these quantum systems. And on the other hand, we have tensor networks, and in there what we do is we exploit the low entanglement of the states that we're usually interested in, like, so that we can factorize the states in terms of matrix product states and other tensor networks and generalizations in high dimensions, right? What I would like to point out, and that I think is really important, is that the machine learning community deals with equally high dimensional problems, right? Like basically exponentially exploding problems, and they battle this exponential curse of dimensionality very successfully with impressive results in a wide spectrum of scientific and technologically relevant areas of research. And what I would like to point out is that quantum and classical many-body physics has not been the exception, and there's a current explosion of papers and new studies trying to exploit these machine learning ideas and techniques to understand physics and to understand many-body systems. So problems ranging from machine learning phases of matter, new inspired answers for quantum many-body systems that are inspired by machine learning. There's acceleration of Monte Carlo simulations, quantum state preparation, strongly correlated electrons, which is heavily pursued in Japan by Professor Imada. This normalization group analysis using RBMs and PCA, quantum state tomography, decoders for quantum computing, the supervised learning inspired with tensor networks, which is kind of like going from physics helping machine learning. There's quantum Boltzmann machines, which is using quantum computers for machine learning. and more, right? Like quantum machine learning algorithms. So it's very exciting, and everything looks very promising. I believe there's a lot of opportunities for us physicists to make progress and to invent new algorithms, basically, and new ideas. And in this talk in particular, I will discuss several applications of these ideas to problems in many body physics in classical and quantum. So the first one is going to be very simple, but it's very basic, but it's a supervised learning approach to classical phase transitions in Ising models. And then the second part is data-intensive problem in quantum mechanics, which is that of learning quantum states, and my approach is going to be unsupervised learning. Okay, so let me first tell you about the supervised learning part. Like a supervised learning perspective on these phases of matter, right? So I'm going to start this with the simplest system that I can think of, which is the Ising ferromagnet in 2 dimensions. So as we all know, this system is given, like the energy of the system is given by this sum over neighbors, where sigma I, sigma j are like basically spins that can take value up or down or plus or minus 1. And what happens with the system is on the square lattice is that in the low temperature regime, this spins tend to polarize up to minimize the energy or down. And as we warm up the system transitions into a completely disordered paramagnet. Okay, so this has been studied by Larson Sager analytically even a long time ago and is well known. And so this is my setup, like to introduce the ideas. Okay, the system has a ferromagnetic transition where the order parameter, the average magnetization, goes from finite to 0 at the critical temperature Tc. Okay. And so, but what do I mean by machine learning phases of matter, right? Like so, and the idea of the inspiration comes from the fluctuations in handwritten digits, right? Like so, there's this famous data set in machine learning where like a big bunch of people just wrote down handwritten digits from 0 through 9. And then the machine learning community developed really powerful supervised learning algorithms that can take as input those images and then tell the computer what the digit was that this person was trying to write. Right? Like so, for instance, here on the right, I have 5 that is written by a human, and then this neural net is able to categorize or to classify this image as a 5 that the computer can understand. And then so my understanding of this was that the 5 here on the left can be understood as a perfect 5 that the computer can understand plus some fluctuations. Okay, and then which sounded to me very similar to what we do, for instance, when we take and understand a phase of matter and we add I don't know, a mean field cartoon for the phase, and then we add some fluctuations arising either from thermal effects or from quantum fluctuations, right? Like, and so that was my motivation. I took this idea, and then we took these phases of ferromagnetic phases and high temperature phases, and then I gave images or representative images of that phase of matter to these neural network algorithms, and then I just try to classify them. And what I do is, yes, I classify a set of images at low temperature that I call 0 or ferromagnetic, and then at high temperature I call them paramagnetic or 1, right? Like so that's the main idea. And so this so I tried that and it worked successfully. So I just basically produce a big bunch of images like this using Monte Carlo sampling with 20K samples below TC and 20K samples above TC, and the neural net successfully learns to distinguish between these phases. And not just that, but you're able to even extract critical behavior. There's finite size scaling that you can apply to these neural networks, and you're able to extract, for instance, critical exponents, critical temperatures. The other surprising thing that we found is that, for instance, if you train one of these models on the square lattice, for instance, and then you take 8 and you try to process data, I don't know, coming for instance from the triangular lattice, then that this neural net is able to distinguish or to identify the critical temperature and the critical exponent. And not just that, you can also even change dimensionality. So for instance, if you take this train model on the two-dimensional system, you can even try to go ahead and try to pin down the critical behavior, for instance, in the 3D Ising model. So it means that the neural net is able to understand and make sense out of the main characteristics of the phase transition that are that we're trying to understand through these neural nets. Okay, so that's a very simple example, and it was successful, and we were very happy. So but it was kind of like a first example of what we want to achieve, which is generate or kind of like discuss a broader perspective on the problem of the condensed matter physics or many-body physics using machine learning. So, but then we asked the following question: can we deal with disorder and topological phases that do not have an order parameter, right? Like which are a little bit more challenging with respect to this simple classification problem? And so we started and we thought, okay, maybe we can try some topological phases, for instance, fractional quantum Hall effect, quantum spin liquids, Ising gauge theories, and these have all sorts of potential applications in quantum computing. And the interesting thing is that they defy this Landau symmetry breaking classification of the phases. So can we use machine learning to understand those? And there's also sort of interesting examples like in Coulomb phases that are also disordered, like for instance, common water ice is one of them, spin ice materials like holmium titanate and dysprosium, and so we wanted to see. So I'm going to show you just one example, is the Wertner's Ising gauge theory, which is basically this Hamiltonian here. It's just basically an energy function that is a sum over the plaquettes in the square lattice, and then the Hamiltonian is basically the products over the plaquettes or the spins on the plaquettes. And this is very interesting. This Hamiltonian has two phases. So the ground state, which is classically disordered, so there's no order, but it is topologically ordered. And then there's at a finite temperature where the system is completely disordered, so it's only two phases. But there's no order parameter, which is very interesting. And I'm going to show you two configurations. So one of them is ground state, and the other one is infinite temperature, right? Like, and as you can see, it's a little bit harder to distinguish which is which, okay? And so this is also more challenging for the machine learning algorithms to distinguish. So here's the result, and so the image on the right is the ground state, and the image on the left is high temperature state. So, but, and what we found out is that these feed-forward, like more traditional neural networks, are difficult to apply to this problem and lead to an accuracy of 50%. So basically, the neural net doesn't know what is going on. But we found out a solution, and through the use of convolutional neural nets. And these are useful, and they just basically solve the problem by just going locally and detecting this constraints induced by the energy function or by this Hamiltonian that we use, and it works, and you get 99% accuracy, and it's easy to train. So that was kind of like also an interesting exercise. And we then tried, okay, can we apply this idea to fermionic phases of matter, like Haber models and so on. So here is an example of the Haber model on the honeycomb lattice at half-filling, where we know there's a transition between a semi-metal and a Mott insulator. And so we wanted to know if this was, if this set of ideas was applicable also for strongly correlated fermion systems, right? Like, and what we found out is that yes, that it works, and we're able to pinpoint critical points, and we're able to even try to attempt to compute critical exponents and so on. We did that then in 3D, for which we used the three-dimensional Haber model, and then we studied the transition between so this is at half-filling, the transition between the antiferromagnetism and the high-temperature phase. And what we did was we trained the models at the extreme low U limit and the high U limit, and then the neural net is able to interpolate along the phase diagram. As you can see, this blue dots and red dots that are predictions from for the phase diagram from the neural networks, and they agree more or less with this calculation by determinant QMC and numerical link cluster expansion. So we were happy. In this case, we use three-dimensional convolutional neural net, and as input we use classical spin configurations coming out of determinant QMC. So okay, so that's interesting. It worked, and so so we wanted to go ahead. So we wanted to see if we could explore an unsupervised learning perspective on quantum states, or trying to see if we can use unsupervised learning to learn quantum states. And my tool or my technique is generative models, right? But let me first introduce this problem in the context of quantum state tomography. So what is quantum state tomography, which is one of the applications that I'm interested in? So quantum state tomography is the process of reconstructing the quantum state by measurements on a quantum system. And it is important because it's the kind of like the gold standard for verification and benchmarking of quantum devices. So you can use it, for instance, for characterizing optical signals or optical quantum signals. You can use it to diagnose and detect errors in quantum state preparation, so that, for instance, you can diagnose problems in the preparation of a state by a quantum computer. You can use it for entanglement verification and more, right? So, and the idea is that there's been a lot of recent progress in controlling large quantum devices, right, like quantum systems. And there's also a lot of progress in the availability of measurements that we can perform on these quantum devices, and they just come with great accuracy, right? So it used to be that quantum systems or synthetic quantum systems were small, and so using quantum state tomography with traditional methods would be enough. But now these devices are growing faster and faster, and this bottleneck in progress in the characterization of quantum devices becomes the curse of dimensionality, this exponential growth that I was alluding to at the beginning of the talk. And here I have several examples of these quantum devices. So the first one on top is, I think, ion-trapped simulators. The second one is Google 72-qubit quantum computer. Here I have a D-Wave 2000 Q device, and the last one is cold atom microscope experiment. So these systems are growing beyond what we can do with the exact traditional quantum state tomography. So but how do we go beyond that, right? And then even more recent, like the synthetic quantum devices that are growing super fast. So for instance, last year in November, we saw a many-body dynamics quantum simulator with 51 atoms in the experiment. We saw then also in November 53 qubits. This year we published observation of a topological phenomena in a programmable lattice with 1,800 qubits. So there's quantum chemistry calculation. So things are growing really fast, and so we need technology to characterize these devices properly, right? The most rigorous way is quantum state tomography. So what we require is a quantum system that can be prepared repeatedly, a set of measurements that we can apply to these systems, and then we need a training procedure and a model, right? That will be the model for the state. And for this we can use either the full density matrix, which is the traditional approach. We can use matrix product states, which is a modern incarnation of quantum state tomography, matrix product operators, which is also very, very interesting, or we can use neural networks and machine learning inspired answers. And at the end, we want to apply some certification scheme, so that we know that what these devices are doing is the right thing. So the typical state tomography protocol prepares many copies of the state, which are then measured in a set of ways, and finally the outcomes of those measurements are analyzed to produce an estimate of the state, raw star here at the bottom of the slide. So how to make the quantum state tomography efficient? So the first approach that I'm going to briefly mention is tensor networks, so MPS and MPO. So what they do is they introduce a parameterization of the quantum state with good scaling and non-trivial structure on the quantum system. So in this case, low entanglement, right? Like, so here we can use MPS, matrix product states, which is basically the answer that is used for, in DMRG. Or if you're dealing with mixed states, you can use MPO, quantum state tomography. And here are two examples of excellent papers: efficient quantum state tomography by Kramer and collaborators, and there's also a scalable maximum likelihood method for quantum state tomography from again Kramer and collaborators, so using MPS and MPO respectively. There's a different approach now, which is more recent and that was introduced by us, which is using neural networks, so in machine learning techniques. And the idea is to introduce a parameterization of the quantum state that has good scaling, again, non-trivial structural information, and that is very easy to manipulate. And here we've used restricted Boltzmann machines for pure states and for mixed states, and this reference number 4. So I'm going to tell you a little bit about the neural network quantum state tomography approach for the case of pure states. Okay, so and what we do is we use this restricted Boltzmann machine, that is a generalization of the restricted Boltzmann machine used in machine learning to complex numbers, because because the wave function is intrinsically complex, right? So, and what this means is we basically have a model for the wave function that is composed of a visible layer in green here that represents the state, that is connected to a set of hidden spins that are not physical, that at the end are traced out, and they interact through some connections given by these black lines, and so on. And then for the phase of the state, we use a different set of restricted Boltzmann machine with a set of different hidden spins in blue up there, which represent the interactions again with the new matrix W mu, and then that they will encode the phase of the state. Okay, and the first state that we tried was a very simple state. The target wave function here is the W state, which is basically a superposition of 1 0 0 0 0 plus 0 1 0 0 0 plus 0 0 0 0 1, and so on. Okay, and what we found out is that we apply measurements on this state, and as a function of the number of measurements that we apply ns, what we see is that we are able to reconstruct or to encode this state out of measurements into our RBM, our restricted Boltzmann machine, for this neural network, and as a number of examples, and as this the overlap between the exact state and our restricted Boltzmann machine just quickly goes to 1. So that's very simple and very nice, and but we wanted to do more. We wanted to add phases to the state, so we add some phases to demonstrate that we can recover a less trivial state, so with some phase and some interference in the state, and we were able to recover the phases that we first randomly draw, and using this set of measurements again. So this is interesting, and it was published in Nature Physics. We also studied ground states of many-body Hamiltonian. So for instance, these are correlation functions for the translocalizing model. On the left, those coming from the exact calculation or the exact Hamiltonian, and on the right we have the reconstructed correlation functions of our neural network. And below you will see examples for correlation functions from the 2D transfer model and for the 2D XZ model, and the agreement between these models is pretty remarkable, right? Like, and so I just emphasize this is learning from measurements on the system, so there's no Hamiltonian or anything else. There's just measurements on a quantum system. Then we use those measurements, we reconstruct the system, and then recompute the correlation functions, and they match relatively well the expected behavior, right? And here is a more interesting example: is that we, by doing the same thing, we can take those systems, then reconstruct the wave function, and at the end compute many-body entanglement, right? Like, which is very difficult to access experimentally. So the suggestion that we're doing here is that we can take experiments, make those measurements, reconstruct the state, and then measurement entanglement, which is basically experimentally, right? Like, so it's just very hard to get experimentally, and so our approach suggests a more viable experimental way of doing it. And here on the left, I have a comparison with a system, a paper in Nature in 2015, where they measured the entanglement for 4 particles, right? Like in here, we're showing that we can scale this approach to much larger systems, right? For instance, for n equals to 20 spin, we already have pretty good results, right? So it's interesting for like experimental reasons, and also because it shows that these RBMs generalize very well, because these measurements are very non-local. Okay, so it's an interesting example. The last example that I'm going to tell you about is a new approach that combines neural networks and tensor networks, right? Like, so these examples that I've shown before, they parameterize the quantum state. Instead, we're going to parameterize the Born's rule, which is the outcome of the measurement, this probability distribution of the measurements. And I'm going to use generative models, right? And the measurements I'm going to use are informationally complete positive operator value measures. And the plot that you see here is a tensor network representation of this answers that we're going to be using for the reconstruction of the state. Okay, so let me go ahead with this, and so we're going to learn mixed states. So this is a little bit more general than our previous approach, and what we do is we take those measurements, this positive operator value measurements, and we generate them in the experiment, or numerically, synthetically generate these statistics, and then what we do is, okay, the relation between the state and this statistics is given by Born rule, right? Like, which is the relation between measurement of an operator and its probability, right? Like here, PA. And what we do is we use unsupervised learning, which is basically a parameterization of this distribution, and then we use that probabilistic distribution to compute P, or the density matrix of the model, which is given by this expression on top left, which is given by this tensor network diagram here. So that's our, like, the model for our density matrix. And the good news about this is that this model can be anything. So it can be all those modern probabilistic models from machine learning, like variational autoencoders, restricted Boltzmann machine, generative adversarial networks, any model basically. Okay, so it's a very flexible technique, and it can be applied in any dimension, basically any spatial dimension. So that's good news. So I'm going to show you results on a synthetic data set for this G8Z states, which are prototypical states using quantum information. We're going to deal with the pure state and then locally depolarized generalized states, which are basically the G8Z state with some noise model of the coherence, right? Like where with probability 1 minus p, the qubit remains intact, and with probability p, an error occurs. So that's basically a mixing term in the G8Z state. Okay. So here are examples of the learning of a 2-qubit locally depolarized G8Z. And what we see here is results from the RBM. And what you see is that the distance between the probability distribution that I'm trying to train and the real P of the G8 state quickly goes to 0. So this is kind of like a measure of the distance between the G8 state and my state that I'm trying to reconstruct. And in B, you will see the fidelity, classical fidelity, which is also a measure of how close this distribution are. And as the training happens, which is this labeled epoch, we see that this quantity goes to 1. And finally, in C, you will see the fidelity, actually, the quantum fidelity, that we also see it approaches 1 pretty quickly for all values of noise, okay? And this is obtained by parameterizing this probability of the measurements with a restricted Boltzmann machine with multinomial visible units, right? Okay. So this is the number of outcomes in this measurement that we designed. Okay. Okay, so that's interesting. This is the G8 set. The other thing that we found out is that the scaling is very favorable, right? Like, so for larger and larger system sizes, we only need to provide a number of measurements that scales only linearly with the number of qubits. So it's cheap. Its scaling is very favorable. And finally, I'm going to show you that we can also learn ground states of local Hamiltonians, which are relevant in quantum information, in condensed matter, and cold atoms. So they're very interesting. Here are 2 examples, right? Like, so here's the transfer field model in 1 dimension for 50 spins. And what we see here is measurements, again, on this type that I was discussing before. And what you see here is measurements on a synthetic state using DMRG, and reconstructed state, which is using this neural network approach that I just discussed, and the agreement is really good. And in B, you see sigma 1, sigma I correlation function, and it's just the agreement is really good. And in C and D, I discussed the 2-spin correlation function for the Heisenberg model on the triangular lattice. And as you can see, it's hard to distinguish or to tell the difference between the synthetic state, which is again DMRG, and the reconstructed state. So it seems to be working also for this ground state of local Hamiltonians very well. So with that, I would like to conclude my talk, and so with the following conclusion, so that we're starting to explore machine learning perspective on many-body problems in classical and quantum physics. In particular, we encode and discriminate phases and phase transitions, both conventional and topological, using neural network technology. We have performed quantum state tomography using neural networks with results that are better than the state-of-the-art methods, and which are enabling us to study 2D and potentially 3-dimensional systems, which are very challenging. I just want to leave you with the following message, that I believe there is a lot of opportunities for us physicists in this field of the intersection between physics and machine learning. And with that, I would like to thank you all for your attention.